Gravity has long been viewed as a fundamental force, from Newton's apple to Einstein's curved spacetime. But a new study by Dr. Des Melvin Vopson, published in AIP Advances on April 25, 2025, proposes something revolutionary. Gravity might not be a force at all, but a computational process, an emergent effect of the universe organizing and compressing information. Rooted in the rising field of information physics, this theory suggests that reality itself, matter, energy, even space-time, is built from encoded data. Gravity, then, may be the universe's way of optimizing its own informational structure. In this video, we'll explore this bold new idea, how it works, and what it could mean for the future of physics. At the core of Dr. Vopson's theory lies a radical yet intuitive idea. The universe operates like a computational system. Every interaction, particle, and even the fabric of space can be expressed as bits of information. This concept echoes John Archibald Wheeler's famous phrase, "it from bit," which asserts that the physical world arises from binary informational content. Vopson introduces a model called space pixelation, imagining the universe as a grid of tiny, discrete units at the Planck scale, each unit functioning like a pixel in a digital image. In this framework, a 1 could indicate the presence of matter, while a 0 signifies empty space. This organization mimics digital simulations where information is efficiently stored and processed. By grouping matter together into more compact systems, the universe effectively reduces the amount of scattered information it needs to manage. This structural ordering reflects a deeper computational strategy, minimizing complexity to enable more efficient updates or calculations of the universe's state. Just as computers compress files to improve storage and performance, the cosmos may be performing an ongoing act of informational simplification, and gravity could be the tool it uses to do so. Dr. Vopson frames gravity as a mechanism of informational efficiency, governed by what he calls the second law of information dynamics. This law proposes that systems naturally evolve toward configurations that are less informationally complex, seeking patterns, order, and minimal entropy in data terms, rather than purely thermodynamic ones. This viewpoint transforms our understanding of gravitational behavior. For example, the way galaxies form from clouds of gas or stars emerge from denser regions can be interpreted as acts of computational consolidation. Gravity isn't merely pulling objects together. It's helping the universe become a cleaner, leaner system in terms of information flow. Perhaps most intriguingly, this perspective may offer insights into why the universe is structured the way it is. Large-scale formations such as cosmic filaments and voids may be emergent solutions to deep computational problems. Instead of seeing gravity as a standalone force, we can now imagine it as the expression of the universe's algorithmic need to self-organize and compute its own evolution more efficiently. This changes the narrative. Gravity isn't something that just is, it may be something the universe does as part of a deeper logic embedded within the fabric of reality itself. Dr. Vopson's theory doesn't stand alone in attempting to recast gravity through the lens of deeper principles. A number of cutting-edge frameworks share conceptual parallels, suggesting a growing movement toward redefining physics as an information-driven science. One closely related idea is entropic gravity, proposed by Dutch physicist Erik Verlinde in 2011. Verlinde argues that gravity is not a fundamental interaction, but an emergent phenomenon arising from the statistical behavior of microscopic information associated with the positions of material bodies. In his view, gravitational attraction results from the tendency of systems to move toward configurations with greater entropy. While Vopson focuses on informational efficiency, Verlinde emphasizes informational disorder. Yet both posit that gravity is not fundamental, but emergent. Another complementary theory is the holographic principle derived from black hole thermodynamics and string theory. Introduced by Gerard 't Hooft and further developed by Leonard Susskind, it proposes that the total information content of a volume of space can be encoded on its boundary, much like a hologram. This idea aligns with the notion that reality is fundamentally informational, and that what we perceive as 3D space may be a projection of underlying data stored elsewhere. The digital physics school of thought, led by figures such as Edward Fridkin and Stephen Wolfram, suggests the universe behaves like a vast cellular automaton, an evolving, rule-based computation. Wolfram's work on a new kind of science explores how simple rules can generate complex patterns, and his more recent physics project attempts to derive space-time and relativity from discrete networks of computations. Even more radical are quantum information-based theories of reality, such as Seth Lloyd's model that the universe is a quantum computer. In this scenario, all interactions are computations, and evolution of the universe is a form of information processing. Lloyd estimates the universe has performed about 10 to the 90th power logical operations since the Big Bang, a perspective that fits well with Vopson's computational narrative. All of these frameworks, from Verlinda's entropic logic to the holographic principle to Wolfram's rule-based space, converge on a striking idea: reality is computation. While they differ in mechanisms and emphasis, they share a belief that what we call forces and particles are emergent, not foundational. This convergence suggests a deeper unifying truth may be waiting to be uncovered, one in which gravity is just a visible ripple on an invisible ocean of encoded data. Future research could explore how these theories intersect, whether through mathematical modeling, cosmological simulations, or quantum experiments. If multiple informational theories converge to similar conclusions, it may soon be time to rewrite the very language of physics, replacing mass, charge, and curvature with code, logic, and entropy. Thank you for watching. Don't forget to like, subscribe, and share this video with fellow science lovers. Got questions or theories? Leave a comment below. We read them all. Until next time, stay curious, stay inspired, and keep exploring the universe.